Hello and welcome to another interview for the Zero to ASIC course YouTube channel. And today I'm really happy to be joined by Peter Kinget. He's a professor at Columbia University in New York, and he's invented this great project called MOSBius, which allows you to do experiments that are relevant to chip designers using transistors that are all put together onto a chip. So it's like a programmable transistor array. And in this interview, we're going to be talking about the design, the kinds of experiments that you can do with it, his teaching experience, and the lessons that he thinks that you can learn from MOSBius. So stay tuned for the whole interview.
Hi, so my name is Peter Kinget. I'm a professor at Columbia University in New York. I teach circuit design, integrated circuit design, more particularly analog and high-frequency circuit design. And in the last couple of years, I've really focused my teaching towards bringing in a lot of projects and practical experiences, including lab experiences. And I think today that will be what we talk about. I also, brought on a class about 10 years ago where we design chips and students tape them out, and then they get also this lab experience of working with their own design, which is a very unique experience in terms of becoming a circuit designer. I did my education in Belgium at the Catholic University of Leuven, and then I came to the US. I worked in Bell Labs for a couple of years. I was also on the West Coast, worked in Broadcom in early days, worked in a startup, but then eventually returned to academia now more than 2 decades ago. So that's kind of a brief intro.
Thanks. And we're both in the Solid State Circuits Society. So that's how we met. And there's the new Chipathon.
Yes.
Happening at the moment. So if you're interested, then check out the Chipathon. I'll put a link to the to that project in the description below. And one of the projects that is happening this year is about MOSBius, and that's actually how I first heard about MOSBius. By the way, took me a little while to realize that it's a Mobius loop with the MOSFET. So, but I really like the name and the logo. Yes. So.
Sorry to interrupt you. The credit goes to the students. Cade actually came up with this beautiful logo, which has the MOS resistor. People will see it in a moment. Yes.
Yeah.
But you got it right. Yeah.
Yeah. Why don't we get your slides up now?
Okay. Well, so here we have a little animation of the MOSBius logo. So yeah, we started with some Infinity, Mobius, lots of opportunities, MOS transistors, so that's where we landed. And so I have some slides here to talk about the project. I like to emphasize that the goal here is to make a platform that students or learners in general and even professionals will enjoy using this. It's very compact, and you just need your laptop, a small USB instrument, and so I kind of joke that you can do your lab experiments now at the lunch table, because of using MOSBius, which I'll introduce now. So here's kind of a brief overview. So in the center, you see the setup, which we use breadboards. We have the chip placed on an adapter PCB in the middle here. And then you wire up some external components in order to make the circuit, and then you have a USB instrument here, and this is really your whole lab environment in combination with your laptop. So I'll talk a little bit about a custom chip that we made in order to support these kind of lab experiments. Our goal really was to enable lab experiments that are relevant to IC designers, so that use techniques, circuit configuration, transistor configurations that you use on integrated circuits, but make them accessible to lab experiments. And so I'll explain that philosophy a little bit in a moment. So why do we emphasize measurements? I think most people realize as they get into electronics, as they get into chip design, that really measurements are an integral part of the design cycle, right? So sure, you need to understand theory very well. You need to be able to analyze your circuits. We have very powerful simulation tools Both of those actually are quite accessible nowadays, right? So you have open source simulators, you have freely downloadable simulators. So there's a lot of ways that you can learn about simulation. A lot of the theory, courses, lots of things are available on the internet. But really the measurement part has kind of been forgotten a little bit. So I want to try to make that way more accessible. And again, within the context of IC design. And, one thing you learn the hard way as you design circuits is that, silicon will do what it wants to do, right? It's a physical device. It will obey the laws of physics. It's not always what you wanted it to do, what you think it's going to do. And even if simulations show certain things, it's really the measurement that is going to prove that your circuit is working the way it's supposed to work. So that's why, I like to emphasize this part.
Do you think that part of your opinion there comes from your work in industry? Because one of the things that I've heard quite a lot from the industry side is that a lot of students leave university from doing a chip design course and they haven't had the experience of doing a chip bring up or lab experiments.
Oh, definitely. And I think it has a couple of facets to it, right? So, first of all, I think a learning experience is only complete if you have confirmed, in the lab what you thought the circuit would be doing, and measured it under various conditions, showed that the circuit is robust, and things, and all these aspects. Secondly, measuring a circuit, brings about a number of techniques you need to learn about, and also will stress or load your circuit in various ways, that if you're only doing simulations, you never think about, because a simulator doesn't add loading. It's like you can see any signal at any time you want. That's not real life. In real life, when we put a probe on something, when we bring a signal out, it will, it can be quite difficult to measure certain things. So measurements is a very critical part, to get back to the physical aspect of silicon design. And finally, also, I think it's very important to do this in school or as part of your education, because the reality in industry is that very big chips, very complicated systems are being designed by very large teams, and often people are specialized and do not get as exposed as much, for example, to the measurement part when they're designers, but you still need to have that background. So it's important to pick it up in school, because in industry, there might not be time to go and sit in the lab and, figure out, what your circuit is doing, because it's part of a big a verification and testing effort that is done by the testing team. And, and you're part of more of the design effort, and you have other priorities. So, I really encourage always students to make sure that they take part in measurements, take part in bring up of chips. It might sound weird, but I think to learn chip design, you might want to start with bringing up a chip before designing one, right? And so that part, actually, MOSBius will also kind of give you a little bit of that experience.
Nice. That's one of the things that we're recommending people to do with Tiny Tape Out, because of the long cycle time. So, like, why not get the students to bring up last year's design, and then you'll know, like, some of the things you need to look out for when you're designing for test. Exactly.
I mean, that's a good strategy. The other side effect here, you probably experienced that, but it will also force designers to actually document their design, right? Because if you are going to test your own chip, you think, first of all, you fool yourself that you think you will remember everything. You don't need to write anything down.
Yeah.
But you're not going to, test your own chip. Somebody else has to test it. You need to take some time to make a data sheet, to write down, how your chip is working. That's also a very important aspect. And so, like, if you plan on, people testing other people's chips, then documentation all of a sudden also becomes an integral part of the cycle that you need to support. And that's a very healthy thing, because also, again, in industry, but I would argue even for your own designs. I mean, I've become a very prolific note taker, because there's lots of tiny aspects and important details that you can never remember all, and so it's good to write them down and create documentation for your designs. Okay, so why don't we jump into? I'll get back to this, into a little demo here, right? So I think it's always good to start off projects with blinking LEDs, right? It's become a standard kind of hello world electronic design. So I have here, a setup that I call Blinky that I can show here on camera. So here is a live feed. I have my protoboard here. It has the MOSBius chip. I'll give you more details later. It's connected here to the breadboard. All the pins of the chip are, put out here on this PCB, so you can access all the pins of the chip, which gives you access to the devices inside. And then we have a little Raspberry Pi here. There is a programmable connections on the chip, and so the digital configuration of that is stored in this microcontroller. And as I plug it in here, I'll plug in the microcontroller. You will see some. You see here the orange LED. That is the clock of the digital data stream. And then the blue is a little hidden, but you see some blue. These were the bits being fed in. I slowed this down. You can do this faster, but now the chip is configured. The enable is on, and it starts to do its function. And its function right now is just to oscillate, and the oscillation can be monitored here by looking at these two LEDs. So this is an analog kind of flashing LED experiment. And so, obviously this is nice. You put some external components in order to make this work. So there's some resistors, there is some capacitor here to make this oscillator. But of course, the learning will start when we connect this to an oscilloscope. You could use your bench oscilloscope if you have those. But what I'm going to use here is something a little bit more compact. So, this is a USB instrument. It has oscilloscopes, power supplies, waveform generators, and also digital I/O, digital inputs and outputs. So I can connect that here to this header, and I will have then two oscilloscope channels, so we can look at a waveform here and a waveform here, and we can start studying what the circuit is doing internally. And so that's what we will see here. Let me load the correct configuration for this experiment. Excuse me. So what we're looking at here is, we kind of see the purple waveform, which is the LEDs going on and off. It's the output of the oscillator. And then what we see here is the orange waveform, which is the internal signal that is loading the capacitor, discharging the capacitor, charging the capacitor, discharging the capacitor. So we see that happening here. These are the internal nodes of the circuit. We can also really study the operation of the circuit. I'll show some slides in a moment, but let me just show the experiment now. So what I can do here, to show you kind of the type of things you can do in terms of learning circuits, so here I'm now opening this switch. The oscillation stops. I opened the feedback loop, so to speak, and I'm going to apply a waveform here. This is a I'll show you. So this is just a triangle wave that is going to sweep the input from 0 to the supply to 2.5 volts. And as I do that, you'll see that we get it's just flashing very quickly. But what that allows us to do is study kind of how the circuit is working internally. And what you actually see is, because this is a relaxation oscillator, you'll see that the upgoing ramp here, the switching happens at this point, and on the downgoing ramp here, you see that the switching happens at this point. And this is called something called hysteresis, and we can actually see that when we make an XY plot. So you see here the characteristic. It's an inverting characteristic, right? So if the input is low, the output is high. If the input is high, the output is low. But as it goes down, it will follow this line, and as it goes, as it goes up, it will follow this line, and as it goes down, it will follow this line. So this here is then a hysteresis window, and that actually sets the oscillation amplitude that we saw before in that in the orange waveform. So you see here that you can now get access to all the internal points of the circuit and really start studying what is going on within the circuit. So what have we been looking at? We've been looking at a relaxation oscillator, which has, you see the characteristic here, this is the ideal characteristic we wanted. If the input is low, this is high, and it will charge a capacitor, so it means it goes up. It moves in the opposite direction, and so as soon as it becomes high again, it will jump back low, and so it will keep doing this up, down, up, down, up, down, and that's what we actually saw. And the way you implement this is, there's many ways to build relaxation oscillators, but kind of a cute way is with just a couple of inverters of different sizes. We insert some positive feedback here in this middle stage, and as long as this is weaker than this stage, then we'll get a hysteresis window that we can use in order to set the amplitude of the oscillation. And so you see here that you get access to all the aspects of the design. So you can think about the theory, you can analyze this, you can analyze this. We also have a simulation environment available. We are using LT-Spice here. So you see the schematic here that you can draw. You label the various nodes. That will then help program the chip. We've made a little bit of software available that will automatically generate the files to program the chip. You saw the Raspberry Pi microcontroller do that. And so then you can compare your simulations to your measurements, and you can really see, okay, there are some differences here. Why is this happening? And you can start studying, and understand what the difference is between a theoretical design and a real-world chip implementation, and start to think about, okay, why do we see these differences, and what could be the physical cause? And you can look at the time domain waveforms. These are the simulations. These are the measurements. You see that, qualitatively, they're very much the same. Quantitatively, there are some differences, and I won't go into the math here, but you can actually explain that in quite good detail as to why this is happening. And in this case, it has something to do with the modeling inaccuracies that we have, or the discrepancy between the amplitude estimation. Once we correct for that, we will get a very good correspondence. So this is very much the cycle, in a very brief experiment here, but the cycle that IC designers go through, which is, you conceive something, you simulate it, you make it, then you measure it, and then you start reconciling the three kind of views: what the measurement tells you, what the simulator told you, and what your analysis told you, and you have to reconcile all these aspects, and then you have a very solid understanding, and you're ready to kind of produce these circuits in larger quantities, because kind of how physical changes in the process will affect the performance of the circuit. And that's a very critical aspect of IC design, because IC designs are, in most cases, geared towards large volume production. So you really need to understand, what the circuit is doing.
So I think, just to make it super clear, if you can go back to the that internal view of the MOSBius chip, do you have a big screen picture of that one? Yeah, that's it. So it's like. Is it fair to say it's a bit like an FPGA, but for analog? It's like a set of N and P transistors, mostly, with different drive strengths, and then they connect all together into this central bus that you can configure in any way that you want.
Yeah, I think that's a fair characterization. So what we have is transistors. So our goal is, it's a programmable transistor array, right? So we have transistors. First of all, they're all accessible on the outside. So, even if you don't want to use the switch matrix, and in some lab experiments, just to, make it a little simpler, we don't necessarily use this. But, everything is available on the exterior of the chip, on all the pins, all the necessary access to various nodes of the transistors is on the pins. And then each of the pins can be connected to the internal bus. We have 10 internal buses. You can think of an internal bus as a node in your circuit. So if you have a circuit with 10 nodes, you can say, okay, at this node, node 1, I want to connect the gate of this transistor, the drain of some other transistor, and the source of yet some other transistor. And then on bus 2, I want to connect this and this and this. And then that's how you build up your circuits in this environment. And so that configuration, then there are actually 10 buses and 65 pins. So we have 650 switches that you need to configure. So you stream in 650 bits, ones and zeros, through a very simple interface here, right? So it's an enable, and then you just have clock edges and 650 data values, zeros of ones. It's fairly straightforward. After you do that, you put enable high, the switches in the middle here close, your circuit is wired up at that point and will start operating, as you could see in my demo.
So you could do it all just externally on the breadboard with wires, or you could, up to a 10-node circuit, do it completely internal to the chip.
Exactly, yeah. So we do both. And also, if you run out of buses, you can just add external wires, right? So most of the time when I do complex circuits, I just make like the easy. Very often I like make the difficult, the lots of wires using the buses, and then there is a few connections missing. Then I do those externally. Or if you have something like a feedback circuit, then it's sometimes useful to do that externally, so you can open the feedback, close the feedback, and have some control over that, as you saw me do with the switch.
Yeah.
So so there's lots of flexibility.
And it seems like for the external components, you don't have any resistors or capacitors on there, so those things have to be outside the chip.
Yeah, we specifically chose to only put transistors on the chip, because any component you put in this kind of architecture requires a pin. We wanted, this is our first run on this, and we really wanted to expose everything that we put there. And so we then said, okay, well, look, if you go around, there's plenty of resistors and capacitors, that you can buy, in through-hole components still today. So, that's kind of a waste of pins. We rather put transistors. What's really harder to find is MOS transistors, small signal MOS transistors. And also what you will see here is that we put here, for example, a current mirror. We put another bigger current mirror here.
Maybe can you just change to slide 16? Because that's a good overview of what's inside. Or is it 17?
Okay, sure.
It's like what's available today.
Yeah, okay. I'll go over this. So let me start with this, and then you can cut it out. So really, what we wanted to do with MOSBius, that where we felt was a need, is that we want to make it possible for learners to experiment with CMOS transistors in circuit topologies that are relevant to IC design. And so if you look at what's available today, you can find some chips which has a low number of matched transistors in this case, or this is the 4007. Many people will know this chip, but it's mostly geared towards making inverters or digital circuits. You can find single transistors, but what you do not easily find is combinations of transistors, so that you can do like circuits that are really relevant to analog IC design, right? So we use OTAs, we need matched pairs for differential input pairs, we need current mirrors, we need a current mirror up here to do all the biasing and so forth. And then this is even a fully differential version of it, a little bit more advanced. But we also want different W over Ls. We want to be able to scale these currents and things like that. Whereas resistors, capacitors, they're easily available off chips, right? So, and we also wanted to make sure that you could probe all the nodes. This is for learning. So you want to be able to look at every internal node, what's happening. And so for that reason, we chose also that everything, is pinned out. And so that led us to the architecture here, where all the transistors are at the periphery. They are connected to pins, and you will recognize here, the current mirrors, the common source transistors. These are small operational amplifiers. What they really is a stage like this, input stage here. So it simplifies a little bit the design of OTAs, that this is already pre-wired for you. You can use it as a comparator. We here have some output stages with stronger drive strengths. So we also came up with a sizing methodology where we define a size of one device as a device that will have a GM over ID of about 8, so at 100 microamps. So it means that if you buy the transistor with 100 microamps, you will get a GM of about 800 microsiemens. And this is a good way to also learn about GM over ID design methodology, and do everything in the relative sizing. That's really a critical skill to learn as well. And so that we encourage that here by talking about relative sizes rather than giving people W over Ls. And then there are the buses, and with the buses you can then create your circuits.
Fantastic. Okay. I'm wondering, should we jump to some questions and then refer to the slides as we need them to answer the questions?
That's great.
Okay. So I've split up the questions into 3 categories, which is where most of the questions came into. And the first category is design questions. So Sylvain asked, is it possible to share the GDS or the schematic?
Yeah, so, well, let me start with the layout. So the GDS we cannot share. So this chip was designed in a foundry process. So this was under...
It's TSMC, right?
It is TSMC, yeah. This was, it's designed in 65 nanometer, but we use I/O devices, right? We deliberately chose I/O devices, so they're a little bit more robust, and also we have 2.5 volts of VDD available. So it makes it a little bit easier to also design kind of analog circuits. You have some more swing and so on. But we cannot share the GDS. We would violate the non-disclosure agreement.
Sure.
That's part of, I think in the intro you mentioned that, this is, MOSBius is also part of the Chipathon this year in 2025. And so, yes, our goal is, we're making a new version of MOSBius. It's still in a proprietary technology, but we are also, now going to help the community. I'll be available as a mentor for the MOSBius track in the Chipathon so that we can start building up a repository of building blocks, of circuits, to build a MOSBius chip. Anybody who wants to build one, can make their own version. That's kind of my long-term goal. But as far as the schematic goes, so I have a website for the MOSBius project. And the website gives us, in the website, I'm giving as much information as I can without violating the NDA. Let's put it that way, right? So it does have, and we still need to work a little bit on building up some further documentation. That's planned for the summer, but then we got dragged into other designs. But there are some chip designs available here. We share some of the information as architecturally and so, but I'm going to try to work some more on including this here. Although I would say that you have a lot of information here, right? So this pretty much tells you the whole schematic of the chip, and the W over Ls are mentioned somewhere else, but you don't really need them. If you know this bias point, you can. I mean, that's what I use when I design circuits using MOSBius. So. We also have a SPICE, right? So we made a whole custom library available. You download this, it's available on GitHub. You open this schematic, you connect it up, and you can run simulations, and you can see how the circuit will behave. Obviously, simulations are an integral part of our design tool. So that's a great thing to have, and it's also very convenient. So I made sure that if you install, in this case, LT-SPICE, but you could do this in other simulators. But LT-SPICE, and you take the schematic, you hook it up, you hit simulate, it will simulate. The models are there, and everything is there. So these are these are models that were available online that are close enough. So they're not perfect, but they're close enough, for you to get a good sense of what the circuit will do when you put it on the MOSBius chip.
Yeah, a follow-up question also from Sylvain was, what's the sizing of the transistor in the analog? So I guess, yeah, just to take one step back, the switch matrix is that all transmission gates?
So, so the switch matrix, I'll just describe it, but it's a little bit described on the website also. So you can think of the switch matrix as a long shift register with 650 registers, right? So that's where the ones and zeros goes, and each of these registers controls a switch between then a particular pin and a particular bus. And we use transmission gates as the switching element, right? So that we can get a good analog connection. We designed them for, I don't recall the sizes, but we designed them for, we try to target between 10 and 50 ohms across process variations. Because if you look, we have GMs of 1 millisiemens. So if we keep all the, this is all nominal, can have more because we have 32 X transistors and so on. But generally speaking, if we can stay within the 10 to 15 ohm range or 50 ohm even, that should limit the impact that these switches have on the behavior of the circuit.
Yeah.
It's always going to be there, but it should not dominate. And obviously there is a trade-off, right? You can only make them that big, otherwise we run out of area, right?
Yeah.
So that's how we designed those switches.
We have the same trade-off with the analog mux inside Tiny Tape Out. Same thing. Okay, another question was, is there a timeline to publish the electrical specs? For example, max current in out of a pin, voltage ranges, built-in op-amp specs and so forth?
I think a lot of that is kind of available on the website. I think it's a good question. I'll think about it, and I'm updating the website on a very regular basis. So I think it's gonna, let me think about it and see how much more I can insert. I will say this. So for ESD reasons, as you could see on the schematic, we have to put some series resistors to give some extra ESD protection to the transistors. And so they will also limit some of the currents. But I can look into providing some more data. We do, for example, I have published a whole set of IDS, so transistor characteristics. What's also interesting, I haven't shown this here, but it's shown on the website. You can use, with even with this USB instrument, you can make a relatively straightforward or let's say simple curve tracer, and so then you can do IDS VDS curves and characterize your transistor that you're really
that is cool.
I thought that was really, it's like really nice to see them kind of develop in front of your eyes. It takes 5 minutes to to set up the experiments, and then you have the curves right there. So in some sense, I think it's also, I'm not against sharing the information as much as I'm allowed to, but at the same time, I think it's also a good motivation sometimes, to just go and measure some of these things and say, well, okay, here, what is the GM? Well, let me measure it. How would I measure GM? Then you have to start thinking, how would you measure these things, right? And I think, because think about it, how are all these models and so on being developed? That's what people have to do, right? And so I've also been talking to some of my colleagues who teach device courses, and they're going to use this and have students measure some IV characteristics and then develop their own models based on the actual measurements, right? Now, that's, that doesn't mean that we can't share some more, but it's also just a good motivation to try that out.
By the way, did you know you can design your own analog or digital chip and even get it manufactured and delivered on this sweet development board? Learn how to do it step by step on my 0 to ASIC course and join 500 other happy chip designers. To learn more, check out the link in the description below. Okay, back to the interview. Great. Okay, so moving on to the next category of questions, quite a lot of people had concerns about safety issue. Not like setting any fires, but like, is it possible to burn up the chip? So two people said, guess you could fairly easily create conflicts or shorts on the internal bus. How robust is it to that? And is there protection against doing that?
Yeah, so right now, so it's always a trade-off, right? So right now, I'm actually an IC designer, but I wrote a little bit of the Python code in order to, to convert your schematic, to the programming pattern in order to configure the switches. Some of these concerns could be addressed if we would build in some short detections and things like that. This is not there right now. So, I also haven't tried, I haven't tried to deliberately burn any of these chips, so I don't know what would happen if you do that, except that I will say that, again, there is a bit of series resistance, let's say here and there, and so the currents would be limited by that. but yeah, I'm not yet in a district. I mean, like I have a limited number of devices, so I'm not kind of ready to start doing destructive testing and see, how I can burn them up. But I will say this: so I have run this lab with the chip with about 100 students in the fall of 24 at Columbia, and we had 20 kits. We made 20 of these lab kits. And as far as I know, none of them actually broke. So they all survived. We put in good ESD. We had students apply 5 volts and the chip survived. So, again, not something I want to do deliberately, but I would say that, by now I know of 1 or 2 things that have broken across various experiments, but that's still a relatively low number, I think. Of course, you can burn any chip. You can definitely burn this chip, and I would caution people. What we also have done on the PCB is we have put a voltage limiter so that you cannot. So if the chip is inside the PCB that we made, you should not be able to apply more than 2.5 volts. So there's a protection circuit there as well. It's not on the pins, it's only on the VDD. But there is also an LDO, so you can just, if you want to be sure not to do anything wrong, you can just apply your power supply to the LDO and use the LDO on the adapter board, and that it will only give out 2.5 volts. So there is various ways that we try to address this, but there's probably ways to do it even better. But if people have suggestions, let us know.
Must have been satisfying running this lab and seeing everyone using this chip that you've designed to do experiments. Yeah,
and the students liked it because it connects. I mean, there is a certain hesitation. So it's interesting, right? So there's, first of all, there's a certain hesitation, towards experiments and all. But once they got the heck of it and they start seeing, like, again, I can draw these curves on the blackboard. Students can see them in books. You can simulate them, but see it like on an oscilloscope right in front of you, right there. It's just different. It's just something that will stick with you. And I think that's a great experience. Secondly, also, you start learning quite a bit of things about the circuit. In order to do some of these measurements, you need to think about how you're going to bias it. Like, many will know about Bode characteristics, right? So Bode curves. To set up the circuit, you can actually measure the transfer function. Requires some thinking about how you're going to do the biasing, and it shouldn't interfere with the measurement. And so we prepare all that material for them. But then they can go and take a look and say, oh, why did I have to put this resistor here, this capacitor there? Oh, okay, and so you learn a lot about the circuit also that way through the measurements.
Maybe while we're on this topic, one of the things I wanted to ask you was if you could share any insights about teaching semiconductors. Like, is this practical element required, do you think, or is there anything else that you've discovered in your 20 years of teaching experience that you want to share?
Yeah,
so a big question, maybe.
Sure. My perspective is that it's also reflected in the slide I show, where you have the three views on the circuit. I would say you have the theoretical, and all the theory and the math, and that's all good stuff, and then you have run your simulations, and that tells you something, and then you have the measurements, and it really a good circuit designer, in my view, is able to connect these 3 things together and to understand, more importantly, okay, simulations are great, but they're just a model of the real world. They don't capture everything. Some of the things are captured with some limitations. The math is run perfectly, but it doesn't mean that the math is representing, the real world. And so you also have to learn how to use simulation, right? So what I tell students is that simulations are great, but the simulator will perfectly answer the question that you ask it. But you have to know what to ask it, right? So if you set up the circuit simulation in a not so smart way, let's put it that way, then it will not complain. It will just run the simulation. It will tell you something, and you will think that this is a valuable insight, but it might not be, because you didn't set it up correctly. You didn't mimic what's happening in the real world. You didn't. What simulation should you be running? I mean, there's always finite time, finite simulation time, finite time towards tape out. Which simulation should you prioritize? Things like that, right? So simulators are great tools, but you need to know what to ask the simulator. And how do you learn that? Well, you'll be inspired by your theory because okay, I'm worried about this, or will this work? But measurements are also a really integral part. As soon as you have built up some experience building circuits, you'll better understand like the effect of parasitics. Sure, the MOSBius platform is on a breadboard, but it's like a scaled version of what you see on a chip. On the MOSBius platform, on proto boards, we have picofarads of capacitance. We use hundreds of picofarads, nanofarads of capacitance. We operate in kilohertz, hundreds of kilohertz. On chip, you might work at megahertz, gigahertz, right, with femtofarads of capacitance, but it's just a scaled version. You still have to worry about, okay, this parasitic versus this, versus how does it affect it? It's not part of the model. Is it part? How do I add it? And so, you're learning all those skills, which are really critical in order to do good circuit design. Because, to kind of conclude, a circuit designer really need to be able to connect those three worlds together. The theory will have limitations, simulation has limitations, measurements have limitations, and you kind of have to combine all of that.
There's no such thing as a perfect current source.
Sure, there is. Well, okay. The first thing I tell students when they use simulators, don't use any perfect currents or voltage sources. Put a series resistor with your voltage source. Even if it's your power supply, there is no. Show me in the lab where you found that perfect voltage source. If you can show it to me, you can use it, but it doesn't exist. And I mean, we can go through many stories of of issues with perfect current sources and things like that. So you should always put some limitation. You should deliberately put some output impedance so that you get.
And that's something that you learn about the fact that simulation isn't the real world.
Yes. Yeah. Not that easy to build a current source in the lab.
Okay, so last category of question was for future. So, for example, are you planning to publish a laboratory manual for other schools to use?
We actually already did. So if you go to the website, right? So I have the website here. So if you look, so it has all this information, and I published the laboratory manual that I use with my students. It's all here. They actually worked off this exact website, right? So what is not here in the public version on mosbius.org are the solutions. But if instructors contact me, I have the solution manual completely worked out here, everything in great detail, and so I will share that with instructors. But no, the whole lab experiment manual is here. This is for a particular type of lab, for a particular course. And what I'm doing now is I've made, the lab kits available. So there are instructions here how you can contact me to order them. And then, we're actually, they're being shipped to me right now. They should arrive in the next few days. I have about 150 of these kits in fabrication. And I'm working with a number of universities across the world, actually, that are planning to use these kits in their fall semester course to offer laboratories. And then we are going to try to expand, I hope that people will work with me, and then we can make lab experiment manuals for various levels of courses, right? So the first course, the second course, and so on. This one is more for a senior, undergraduate seniors or beginning master students. This is a little bit more geared towards that. It's about feedback and stability and two-stage amplifiers. Although the first couple of ones here with current meters and so on are more the basic circuits as well. But we hope to expand this and have people help us make these lab experiments. Then we'll publish them here.
Another question was: are there plans for design contests?
Yeah, so it's all a matter of how much time we have. I would like to do it. I'm actually planning to make kind of so one of the challenges right now is that I do have in about 150 to 200 chips. And so, I kind of I'm thinking about how I can, get as many people, exposed to them. And so that's why I'm working with schools primarily, so that they can, show it to their students in their labs. But I'm also going to make kind of a set of, I think, 20 of these lab kits that I can lend to people if they want to run, say, a design contest. I was also talking to some of the IEEE conferences that run tutorial sessions for students on IC design, and we are thinking of probably in the so 2026, in kind of the spring of 2026, in one of the conferences, we are starting to debate to think about how we could have the tutorials and then have a lab session, so to speak, or measurement session, or demo, or maybe contest, right? Using MOSBius as part of the conference tutorial session. So no, I think these are great ideas.
Another question was, is there plans to do like a mixed signal design, like have a MOSBius paired with an FPGA all on the same board?
Yeah, so I think that would be a great way of building mixed signal kind of experiments. So it's just that I haven't had the time to to build that up. If anybody's interested, I'll be very happy to work with them. It's mostly a PCB design effort, and obviously I think PCB design is just the start. It's then all the integration you need to do, and the setup. I'm sure you also know that, right? All the files and the software, and so to make it really easy to use for people, right? That takes a lot of time. But it's definitely a possibility. So one of the experiments that I do and show is a I'll just show the slides, but is a delta sigma converter.
Well, let's just hold back on that, because I wanted to just get to that in a minute.
But in any case, let me add a phrase. You can so yeah, the mixed signal would make a lot of sense, because you would then in modern design, you have always analog and digital collaborate, and then if you're FPGA, you could do the digital, and then the MOSBius could do the analog. So it would be a great environment to create, definitely for more advanced kind of experimenters or learners.
Yeah. I mean, you do have the RP2040 on that board, and you have the USB device that can be a waveform generator and stuff. So you can probably do a lot just with those two things. You don't necessarily need an FPGA on there.
No, but if you wanted to do some real-time decimation or something like that, or or you wanted to build a SAR converter in real time, but you could use the Raspberry Pi as well.
Yeah. So I've been thinking personally, can we do a small version of this, probably with less pin, have the bus pins be external and maybe only 6 buses for tiny tape out, because we only have the 6 analog pins, but then still be able to have the different size transistors and a switch matrix of transmission gates. And then that would also be a way of growing the audience for this, because we could include it on every tiny tape out chip. So Mike was just wanting to know your opinion on that. Think it's a good idea?
Yeah, I think it's a good idea. Like I said, our initial, but there's many ways to go about this. Our initial point was I wanted to make sure it could be used without a digital interface, and so that's why I exposed the device pins. But you could also kind of quote unquote invert that thinking and say, well, we're always going to program the switch matrix, and you're always going to use the switch matrix, and then you could say, well, then I'd rather use the pins for buses, right? And then
for the nodes,
for the nodes, and bring those out, and then and then have the devices internal, and I can't see them unless I connect them to a bus. I think it's a good way of thinking, and you definitely run with it. Our switch matrix is also kind of very how would I say, most straightforward you can think about. I mean, we just made a crossbar. I mean, frankly, we designed this chip in a fairly short time. We had an opportunity, of silicon available in short time, so we just went for it, right? And so, and we tried to do as much as we could in the time available. With more sophisticated bus designs and associated software, you might need some mapping software and things like that. There's definitely a lot of opportunities. One thing I will say, though, is that you should not underestimate the size of the of the transmission gates, right? So if you want to make them low impedance, they are bigger than the register than the flip-flops, right? So we just did a design, and I remember numbers for that. The total area of a unit is, let's say, 1. 2/3 of that is the transmission gate. I mean, it's all a design choice, but in order to again keep the drop across those resistors in the millivolt range, tens of millivolts maybe, you end up with fairly big designs, because you don't know where people are going to put these switches, right? And so they're in a critical part. They could limit it.
I think it's. I'm going to see if we can do it. So I think it's worth an experiment.
Oh,
and
no,
to draw this to a close, I thought it'd be fun to look at your Delta Sigma lab experiment, which I thought was like a nice advanced lab experiment, and then just have a look to see whether like that kind of thing would be possible on a tiny tape-out version where we only have 6 bus pins.
Let's try this. So here, so this is the breadboard for the Delta Sigma setup. So you will recognize, again, you have the same MOSBius chip here, nothing different. And then in this case, I put the Raspberry Pi up here, which has the configuration and is going to feed in the bits. It's going to go much quicker here. So when I plug it in, you will just see it flicker for a short term, and it's already programmed. So what we now need is a clock signal. The clock signal is going to be generated by the USB instrument, and it will also have an input signal. The input signal will come here. And then I have oscilloscope probes to look at a couple of different things. This is the output, and this is the input signal. You could also look at intermediate nodes here, that are also exposed. What you can see here is that all the connections, a large number of the connections are done on the chip, and then a couple of connections are done externally for 2 reasons. One, we started to run out of internal pins. Secondly, I also wanted to have some ability to open the loop and things like that to do more advanced experiments and characterizations. So if I now, these are going to be the input signals. So I'm going to apply a clock and an input signal, and then we'll look at the oscilloscope. And we'll see what we get. Well, of course, I have to plug in the instrument. Sorry about that. Okay, so now we have the Delta Sigma working here. How do we know it's working? So what you see here is the input signal. It's an analog signal, and a Delta Sigma converter. This is a first-order Delta Sigma converter. It's a 1-bit converter. So it's going to try to approximate this analog waveform with a 1-0 digital waveform. It has really only the ability, or what it will do is it will change the density of 1s and 0s in order to make an approximation to this analog waveform, right? So it does this at much higher frequency. And if you low pass, if you low pass the purple waveform, the output, you will get back the analog waveform. Now, this converter is actually inverting. So when the signal goes high, it tries to make a low signal. So you see, it has longer zeros here, more zeros here, because it wants to create a high. And then in the middle here, we're trying to make, in this case, we're trying to make something close to the middle. So you see that the 1s and 0s are almost equal. Now, this is a little bit of a rough picture here. The way you really look at this is in the frequency domain. So let me change to the a little bit higher clock frequency, which is better for the frequency domain picture. So if we look at the spectrum analyzer, here, what do we see? So let me first show you the input signal. So this is the input signal. Again, we're using a USB instrument that's very affordable. Of course, it has certain limitations. So we're looking here at the dynamic range of over 60 dB already, which is pretty nice. But we see that it's not a perfect input sine wave, but that's okay. And so we do see that our Delta Sigma converter does a very good job at representing all this low frequency information here. As you can see, it mimics it very well. And then all the quantization noise is actually people call this shaped, is shaped to higher frequencies. So the clock frequency is 100 kilohertz is here, and the quantization noise is shaped out of band. It's not here, but it's moved to higher frequencies. And then in the digital domain, you use something called the decimation filter, and you will cut off all this high frequency information and all this high frequency noise and only maintain the signal part. And so, here we see the delta sigma, doing in action, and it's actually working nicely. And now we can go off and do all kinds of experiments. We can maybe make the signal a little higher frequency, and see how the spectrum changes now. So we see that it moved to higher frequencies, and the delta sigma is still in band. It's still nicely converting this. So this now gives you the opportunity to study delta sigma converters. Let me show you a little bit what the topology is, and how we build it in MOSBius. So a delta sigma converter, in this case, it's a first order. So it's this circuit up here. It consists of an integrator, a comparator, and a D flip-flop, which is a 1-bit sampler. Really, it's driven by a clock, and then we have a feedback digital to analog converter, a feedback DAC. Now, when you implement this, it turns out that this all can be very compact. An OTA, resistors, capacitors, resistors. This is the integrator part. This is the summing node because the currents will sum. This is the comparator, and here is a D flip-flop. And so this is how this was implemented on MOSBius. It turns out that we literally used all the transistors on the MOSBius chip. We used all the buses and then some external connections as well. But it is possible with this MOSBius chip to then create this whole circuit. And you saw the measurements already, right? You saw the board.
Yeah.
Do measurements. You can verify the theory. So this should be 20 dB per decade. It is 20 dB per decade when you measure it. And you can go further. So really, to evaluate these things, you should calculate SNR, signal to noise ratio, signal to distortion ratio. And to do that correctly, you actually have to sample the digital waveform and take the digital bits either into, say, Python or MATLAB or something like that, and do some signal processing on. Or maybe you can hook up an FPGA and then do that real time and build a decimation filter, in digital and so forth. So it's really a great opportunity to to learn about these more advanced. This is more graduate level concepts, but you can learn them here. Slightly lower frequencies, but this is all. This is all the aspects, all the physical aspects are present here, so you will learn about all of them. And you mentioned tiny tape out with six pins, right? Mm-hmm. So if you look here, yes, I mean the interfaces are limited. So you need a clock, you need a reference, you need an input, you have an output. So from that perspective, you don't need that many pins, right? Mm. So you could definitely build a block like this, on a 6-pin device. But you need VDD, VSS, so you're going to get there soon. Of course, the reconfiguration, you have to think about how you're going to make it reconfigurable and which aspects you're going to make reconfigurable, if that's something you want to do, in your experiment.
Great. Okay, so let's just start wrapping this up. What's the best way for people to get in touch with you if they want to find out more about MOSBius or get hold of a kit?
Yeah, so I mean, I would go to mosbius.org and look on the left sidebar. It has how to order and how to contact me, and generally my email is there, so you can send me email. You can find me through Google as well. Being at the university, we have a pretty public profile, so just send me email and
fantastic.
Take it from there.
Okay. So thanks very much for your time today, Peter. Really good to find out more about the project, and really looking forward to seeing how it proceeds.
Yeah, it was fun, and thanks for the opportunity. So I look forward to hear back from your audience and see what they have to say. So I'm really open to collaborate with people. So that'll be great.
Fantastic. Okay, thanks very much.
Okay, bye-bye.